Okay, so we're into the dark world of speech recognition now. Um, I was a postdoc here in 1991. I arrived on the 3rd of January 1991, and I was actually, for that time, I was actually only here for 18 months. But it's kind of had a huge impact on my life, and it's working with Morgan has really shaped what I do in research ever since. So I think, just before I talk about this, there's a couple of things I've tried to learn from him. First, I think he has exceptionally good taste in research, and he chooses really good problems, and he thinks about them hard, and it was just great to be part of that group. And as I'll talk about later, to be part of a group which was trying to build a supercomputer, or actually built a supercomputer, and improve the state of the art in speech recognition is just phenomenal. Secondly, as was said several times, his skepticism is actually what makes research actually meaningful, and I've tried to learn from that skepticism as well. And the focus on making things work. So I love being in a group called the Realization Group, because this had a real kind of, like, from the name of the group, you knew you had to make things work. I usually failed, but other people succeeded. So I've called this star NN because there was a kind of running joke. So I should say, most of this talk, I'm back in 1991, 1992. But I think, as I'll try to say, I think it's not a bad journey back in time to take. And if you go to speech conferences, most of the community appear to have taken that journey, although some of them are doing it with more knowledge that they are taking that journey than others. But I think it's a good journey to take, and we can learn some things, and we can do things. So there was a kind of running joke. I think it was, well, I know it was because of TDNN, but then there was all these other things. There was BDNN and CDNN and so on. So I thought I'd call this star NN. But, I like to kind of surf zeitgeist, so I thought I'd better just call it DNN. But that's decades of neural networks. Okay, so things were really, really different in the 1990s. We used to spend a lot of time training big neural networks as acoustic classifiers. We used to use HMMs for kind of fairly limited sequence processing. I was in Berkeley, and kind of across the Atlantic in Cambridge, RNNs were starting to look attractive as large-scale acoustic models. We worried about things like speaker adaptation, how to model acoustic context and robustness. And we had these fancy vector processors to train networks quickly. So that was the early 90s. A few similarities to where we are today, perhaps. I've kind of taken the opportunity to read these papers, but this is actually my favorite paper. Actually, the content is just really great because it's a very nice summary. It has a beautiful title, but it even has an even better final sentence, which is wonderful. But if you actually read the abstract, you see this is paper from 94, it's probably written in 93, training neural networks with over 1 million connections and a speech corpus with over 6 million training examples. So if Moore's law applied to speech, then by 2015, we'd have been training networks with 16 billion weights and 96 billion examples. And I don't think anybody's really quite doing that at the moment. And so if we kind of take this trajectory, the fact that what was frankly a small academic institute in Berkeley and was kind of like the new kid on the block was doing this was brilliant. So not much has changed, and I'm contractually obliged to show the photographic evidence, of course, that not much has changed. Okay, so what I'm going to talk about, actually, in contrast to the previous talks, I'm a speech guy, so I'm really specific about things. So I actually want to talk about context-dependent acoustic modeling. This was sort of the difference, right? This in the kind of in the received history of things of how neural network acoustic modeling worked. So sort of like, you know, 93, 94, kind of the neural network approaches and the GMM type approaches were quite similar in performance. But then sort of, you know, people started to develop context-dependent GMM-based systems, and that started to give the kind of gap in performance. And there was speaker adaptation, MLAN, and so on, but I won't have time to talk about that. So then it was largely context-independent neural networks. There's a bit of context dependence, and I want to talk about that. Whereas now there's kind of two big differences. Well, I mean, there's, as I'll say at the end, I think there's actually other things which are really very interesting. But the first two big differences, which are the kind of famous 30% improvement, 20% improvement, 15% improvement, depends on your baseline. But the famous improvement basically comes from the depth thing, and I'm not going to talk about that. Maybe Brian might have a few words about that, and maybe he won't. And the width thing, and in particular the width of the output layer. So the thing that we never did, I don't know if we even really seriously considered whether we could do it, was to have output layers which were like 12,000 units wide. And in some senses, that was of the things that you know, have happened in the last few years. That's been a kind of major thing. So that appears to be the big difference. We can model context dependence. We do it in a very boring way, right? We take what GMMs do, and we just, you know, you don't have to do this, but the easiest way to do it is you train your best possible GMM system, and you kind of use the alignments from that and the context-dependent states from that for your model. But we were doing context-dependent modeling then. There's a shamefully undercited paper. I checked on Google Scholar. It has something like 18 citations or something. So, I mean, if everybody just went away and cited this is the top paper. It's in Neural Computation, 91 or 92. If everybody went away and kind of cited that in the next paper, that would sort of double or triple its numbers of citations, and that would be a good thing to do. So this was this factoring networks by a statistical method. So that's the short neural computation note, and then there's an ICASP paper which we had in ICASP 92, which was this CDNN, context-dependent neural network for continuous speech recognition. So that was really Morgan and Hervé who did that work. Chuck and I were co-authors. I'm trying to remember what I did. I actually looked at the paper, and I kind of really worried that I was the person responsible for the experiments, because if you look at that paper, the experiments is like one paragraph at the end, and it's really pathetic, and it looks like whoever was doing them didn't finish them in time before the deadline. I can't remember, but it's possible. It's possible. But this was kind of neat, and there was this factorization, which I'm going to argue is actually one. You know, it's not the only way, but it's not a stupid way to do context dependence. So you kind of factorize things into the probability of your kind of monophone given the acoustics, and then you have this conditional probability of the context classes given the monophone and the acoustic context, and that's kind of a neat idea. After I left here, I went to Cambridge, and I was working with Tony Robinson and Mike Hochberg, and we'd read this stuff. Well, I'd read it. I'd supposedly written it. But so we kind of did this for recurrent neural networks. It was a bit of a clunky architecture because, you know, this is our usual monophone thing, and then we had this whole bunch of perceptrons. We kind of had like one perceptron, so this is just a single layer thing. We had one perceptron per monophone estimating the context things. But we did it, and this was in the kind of DARPA 1995 evaluation. By the way, I'm so firmly from Dan's bake-off era that I'm incapable of giving talks without having numbers where differences of 1% are kind of like causes for celebration. So we did this, and it actually wasn't working so badly. It wasn't working so badly. We kind of got these reductions. Meanwhile, not far away from here, there was another variant of that. So this is work that Horacio and Mike did, and this is their feed-forward version of it. Quite interesting because it's sharing the hidden units between the context classes and the context independent. And we'll come back to something not 100 million miles away from that fairly soon. And this was from their paper around the same time. This was working in RM. And again, it kind of worked. So the kind of narrative that context-dependent modeling completely didn't exist for neural networks at that point is not completely right. I mean, sure, it wasn't one shouldn't get carried away here. The degree of context dependence that was being done in these methods was a kind of lot less than was being done in GMMs. I don't know about the SRI work, the stuff we're doing at Cambridge, it was certainly within word context dependence, and that's a real limitation. And we had relatively few context classes, so we'd be looking at just like certainly less than 1,000 context-dependent states, which is a lot smaller scale. And just the way you could parallelize these GMM systems was important. Whereas now, as I said, we kind of take the however many thousand context-dependent states you want and put them at the top of a multi-layer perceptron, which I believe if you have more than 3 hidden layers is called a deep neural network. And we train the thing using backpropagation. It's all extremely familiar. We don't use QuickNet in Edinburgh, but certainly, definitely, possibly they changed this year, but definitely till last year, people in Cambridge were still using QuickNet for their DNN training. So code does survive. So that's what we do. So the question is, well, why do we want to model context dependence? And if you think of it from the sort of GMM point of view, then there's 2 strong arguments. One is that it's a kind of way to get more detailed modeling of the acoustic space. So you do this kind of divide and conquer thing, and you kind of, as you get more training data, you can chop it up into smaller pieces. And, for generative modeling, that's not a bad way, particularly when you've got this kind of sort of flat and sort of local model like you have with GMMs. This is a very sensible thing to do. And then the kind of big thing is that you get this context-sensitive phone modeling. And this is really important because it enables you to use acoustic and phonetic context to discriminate between phones, which would otherwise be highly confusable. So, and it really, really works. We all know this. One of the things to kind of notice, though, is that neural networks, in the way we kind of use them, and I don't want to kind of confuse the issue. I could do, but I don't want to confuse the issue to think about discriminative training for GMMs. I don't think it's going to change a fundamental argument. But neural networks really do focus on the class boundaries rather than within class structure. So that kind of weakens, in some way, that kind of motivation, I think. And in particular, I think there's a few drawbacks of just training a neural network to these context-dependent states. So one thing, and here I'm really talking about sort of frame-wise cross-entropy training rather than sequence training. And I think what I'm going to say is still a bit of an open issue for sequence training, which means we haven't done those or are doing those experiments. But one of the big issues is that when you do this discrimination, it isn't making a distinction between the same phone in different contexts and different phones. And arguably, that is, in terms of discrimination, those are kind of different things. And maybe you're not doing the best possible modeling doing that. Of course, if you chop things up, you do have this data sparsity problem. And there are ways to kind of avoid these problems. To some degree, sequence level discriminative training can help to avoid these problems, and I think the factorization method can help to avoid these problems. I want to talk about another way that we did, which I think has some relevance to some of the work that's been done. So, one thing that, so far as I know, wasn't around in 1991, 92 was the notion of multitask training. I think that came around with Rich Caruana in the later 90s. So we were interested to kind of do multitask training for our context-dependent acoustic models. And what we thought would be the interesting additional task is, in addition to doing the context-dependent state training, we gave the additional task of doing distinguishing between the monophone inputs. So in this case, we didn't even bother using kind of monophone states. We just used the monophone phone classes. So we had 41 in these experiments. And you can kind of think of that as sort of 2 things. One thing is that it's kind of forcing the internal structure to learn features which are about the important discriminations, which are the discriminations between monophones. And that force doesn't really happen if you're just training for context-dependent targets. And you can kind of think about it as a regularizer. So one of the things that came to our mind when we were doing this is so you can do various pre-trainings. You can do kind of the I'm going to say the kind of now quite old-fashioned unsupervised RBM pre-training. You can also do kind of discriminative pre-training. So you could, the thing people call curriculum learning, you could kind of do a pre-training where you learn to discriminate monophones first, so you kind of get the features that are extracted to optimize monophone discrimination, and then carry on to do your context-dependent training. And of course, you could do that as an alternative to multitask, and you could combine it with multitask learning. So that's what we did. And I should say this is joint work with my colleague Peter Bell in Edinburgh. So does it work? And as I say, I've got to show numbers, so I'll show numbers. So we do loads of work on this task to do with TED Talks, transcribing TED Talks, which is quite a nice task to work on because I think it's big enough to be meaningful. It's about 150 hours training data, but it's small enough to be able to turn around experiments with a reasonable pace. Plus, there's kind of standard test sets, and we work on it a lot. So when we do that, this is kind of one of these kind of daemon graphs where you have to be very aware of the numbers on the y-axis. But we find that we get about 5% relative improvement when we go from our baseline, so just to see the context-dependent system, to multitask training. If we do the monophone pre-training, it doesn't kind of wipe out the difference. It in fact enhances things. So that's sort of nice. We can go on and we can extend things. So we like to use these things called, they're a kind of tandem feature. Another legacy of ICSI that we learn from, and this is another. If I'm going to have a minor rant, this is a kind of another point that there is this. Again, there's this whole narrative that nothing happened in neural networks between 1992 and 2000 and whatever it was when these things happened. Well, actually, there were these things called tandem features, which several people in this room were intimately associated with, which people started to use in about 2000. I think, like all the best things, they weren't actually done. Maybe you can correct me if I'm wrong. My interpretation is that they weren't done for the purest of scientific reasons, but they were done to kind of fit in with certain things. But if you actually look at the numbers on the way speech recognition improved between like 2000 and 2008, I think that along with something like FMPE is probably the most impactful single technique in terms of reducing word error rate. This has kind of been erased from the history, and people certainly don't use them as their baseline system for when they want to compare the performance of things. So that's a bit of a shame, and it's also a bit of a shame that kind of people like František Grätzel in Brno and so on. Actually, if you look at their papers, he was developing deep networks then, but he was developing it. This is my interpretation. He basically added a layer per conference, but if you look at these papers, he was getting quite deep. Anyway, that's a digression. We kind of thought we should do a proper baseline, so we do these MLAN features, which is just a fancy name for kind of out of domain bottleneck features, but we really find it helps with domain adaptation. And of course, if we use MLAN features, everything improves, and the difference between the multitask and the baseline decreases, but it's still 3% relative. And even as a speech researcher, I kind of, we don't open the champagne for 3% relative, although it is significant. We're still working this. I just kind of wanted to give a kind of snapshot of a work in progress, partly because I think it has such a nice link to the work that was being done back in 1992. So I guess one thing I learned from Morgan is this kind of view of kind of practical optimism, with an emphasis on the emphasis on the practical and an emphasis on the optimism, I guess. So again, do I actually believe that it's all kind of been done? So certain people will tell you that kind of LSTM recurrent networks have solved the sequence-to-sequence mapping problem, and we can kind of all go home basically. And I don't actually think that's true. And I think I just kind of last night I just thought I'd just kind of randomly write down. So I was concentrating on kind of practical things, which I think working in these deep architectures has kind of opened up the research area again. So a lot of these things aren't kind of new problems or new approaches, but they'd kind of stopped. And going back to them with a kind of, I think, a fresh insight and fresh enthusiasm, because I think people are really enthusiastic again about kind of doing this sort of, maybe it's to do with neural network models or something, which kind of breeds enthusiasm. But there was like real enthusiasm in like, 91, 92, not just here, other places as well. It was really there. And it's kind of back again. And, I think there's a lot of interesting things. So people, going back to stuff, actually optimization algorithms for large scale networks, which was, we kind of thought in the late 80s that yes, gradient descent's just kind of stage one, within a couple of years, we're going to really hammer this. And we kind of all, I spent kind of a few months of my PhD reading optimization textbooks, and like other people, we tried these things, it didn't really work. But stuff is actually happening now. And if you look at, like the Hessian free optimization things, it's very interesting. And there's kind of various other things that I think are kind of, I think just opening up the research field. So, it really is true that the framework for modern acoustic modeling sort of happened here. What was it? I don't know, 24 years ago or something, which I think is excellent. It was just so cool to build the RAP. It just made things that you could actually do these experiments. This is the reason why I was desperate to come here as a postdoc after doing my PhD, because I kind of knew that I could actually do stuff which I couldn't do anywhere else. So you kind of have these ideas, but then you kind of spend an awful, in those days, you spend an awful long time waiting for something to train on Timit, and it was a very slow experimental cycle. We actually, for that point, we just had an amazing experimental cycle compared to, Krista showed you the kind of graphs. And it is worth kind of going back to look at things that were done in the past. Those papers are quite interesting. So I'll stop there. Thanks. Yep. 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 Yeah. 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 I should add that one of the problems with the factorized thing is that decoding is a little bit more expensive. Depending how you do it, it can be a lot more expensive. So that is an issue. Yeah. Yeah, you could. We didn't, but you could. Yeah. Who are they? I don't know where it is. Well, the only person who wasn't here last night was Phil Cohn. Who? Oh, and David Bailey. Sorry. Yeah.
Steve Renals, Andreas, Krista, Jim Beck, me, Chuck Wooters, David Bailey.
Yeah. That was the RAP users group, apparently. Absolutely. I think that was a 4-board RAP. Because there were also RAP stations, which was a RAP board in a Spark 20. But that was a kind of neat idea. But I kind of had one on my desk, but I always use the 4-board RAP because it was like 4 times faster. Oh, you mean the kind of things people called acid H and N, that sort of stuff? Yeah. So the one. Yeah. Yeah, I think it's I think there are several interesting things to look at. So is that the thing I mentioned, this acid H and N thing, which Michael Finker and Jürgen Fritsch did, which certainly in the 90s we found really difficult to replicate, but it was a cool idea and could be worth looking at it again. I think it was just hard to train properly. So yeah, I think I actually seriously believe it's worth actually reading those papers from the 1990s because there's some reasonable ideas there.